Today's lecture, we will, after having had a lecture on oxidation reactions and reagents, today we will talk about reductions. And this is, of course, in principle, a type of reaction you should be very familiar with, and you have seen various types of reductions through all your organic chemistry lectures. And with this 2-hour lecture, we will try to add some new methods and also to get a little bit order maybe in the types of reductions you can achieve. The two most common functional groups we usually think about if it comes to reductions are carbonyl groups or carbon-carbon double bonds. We will see some examples that there are functional groups like epoxides, alkyl halides, which you can use for reductions as well. But very often, we are looking at the reduction of carbonyl derivatives. And just to give you a summary here, in the end, the types, in the beginning, the types of reductions one might be interesting is carboxylic acid derivatives. And the three I would like to mention at this point here are acid chlorides, esters, and also amides. Typical reduction products you might look at are aldehydes, alcohols, or the hydrocarbons here. And as we have discussed already in the when we talked about alkyl lithium and alkyl magnesium compounds, one of the key features or one of the problems you would like to address is chemoselectivity. So what you're interested is the selective reduction of one functional group in the presence of another. And we will see some very interesting examples, I believe. The one thing you, of course, I'm sure you already realize is that you have a good chance to selectively reduce or react a more reactive carbonyl derivative in the presence of a less reactive carbonyl derivative. But you will see that you can even reverse this type of stigma I've just put forward. And the other type of chemoselectivity you are interested in is that you achieve the selective reduction to one reductive state of the compound rather than the other. So for example, you are interested that you can reduce an ester to an aldehyde and not having it go down all the way to the alcohol or the other way around. And so these things are especially important or especially relevant when it comes to ester or acid chloride reduction. You will see some methods. We will cover one that you can very effectively reduce carboxylic acids all the way to the alcohols. And again, what I just said is very often you are interested of achieving, for example, ester to aldehyde, but also ester to alcohol directly. And let's put up some other functionalities you can easily reduce. Are nitriles. There are methods to make either the aldehyde or reducing it to the amine. If you have, you can see that this can easily become a little bit confusing if you have amides here. There's also a possibility to take them down to the amines right away. And another very useful group to come to amines is the nitro group, where you can go to the amine as well. And then if we take this down to the carbon-carbon multiple bonds, we have triple bonds. And here the reduction to alkenes plays a role. And again, stereoselectivity comes into play. One is interested in selectively achieving either the cis or the trans alkene. And of course, the complete reduction to the alkynes is also important. And very often in these type of processes, you create stereocenters as well if you have a prochiral center here. So issues of diastereoselectivity, but also enantioselectivity play a role here. This is a very crude summary of typical problems you look at. If you look at the reducing agents, the trend I've written here is that you try, with the carbonyl compounds, you try to reduce a more hard functionality. With the double bond functionalities, you are more on the soft side. And so typically, the reducing agents on the hard side, which you use then, are hydrides. So lithium, aluminium hydride, sodium borohydride, a lot of reagents you know here. On the double carbon-carbon double bonds, usually it is hydrogen you use in combination with a transition metal. And typical transition metals that are used here is palladium. That's probably the one reaction you know best. Palladium on charcoal gives a very good hydrogenation catalyst. But a lot of chemistry is done with rhodium and ruthenium. These are generally relatively expensive metals, especially when it comes to rhodium. Rhodium is more expensive than gold. And so there are other developments. Nickel is long established as a metal which you can use here. Cobalt. And especially more recently, there's a lot of effort to develop iron as all types for all types of catalysis. The dream one has here is that one can replace chemistry, which is affected by palladium, rhodium, and ruthenium with iron, and you all know that iron is abundant on Earth, so that if that would be possible, and there have been during the last 4 or 5 years a lot of exciting developments to show that reactions you formerly thought are only possible with these more precious materials, metals, can be affected with iron as well. So I believe we will see during the next 5 to 10 years some very exciting developments in this area here. Another very important and also exciting development is, if you look at these two reagents you use for hydrogenation, it's hydride or it's molecular hydrogen. Both of these reagents are not optimal, especially from a safety point. Think about this. Already when you do, I'm not sure if you have done it already in the lab, do a reduction with lithium aluminum hydride, you have to be extremely careful, even if you use only a few grams. If you do this on a ton scale, this becomes a big issue in terms of security. Lithium aluminum hydride is pyrophoric. You have to quench it very carefully after the reaction to make lithium and aluminum hydroxides. You create a lot of waste. So that's not trivial. On the other hand, here, hydrogen, which is of course a very clean reagent, and ultimately we think we might be able to drive our cars with this one day, is also not easy. Very often you need high pressures, but hydrogen, of course, also very often is easily, has always the danger of creating explosions, especially if you have oxygen somehow brought into the system. And if you have then your metal vessels also, very often hydrogen can ignite on some kind of a metal impurity or metal which is in your reaction flask or reaction vessel. And so that's also not the ideal reducing agent. What comes up here more and more is that people discover that you can use alcohols as reducing agents. And alcohols in the way that you do a transfer hydrogenation. And we will see an example of this in more detail towards the end of this lecture. But just let me lay out the concept. The idea here is that you can take a unsaturated functionality like a carbon-oxygen or also carbon-carbon double bond, use your alcohol as a hydrogen source. Maybe I... And then effect the reduction by simultaneously oxidizing the alcohol here to the corresponding aldehyde or ketone. And very good reagents for this, very inexpensive, which then you can use in excess, because I believe you clearly see that these type of reactions might be reversible, so you have to drive it over to the right size. This can be very often affected by using your alcohol reagent in excess. And there are very simple alcohols available, inexpensive, isopropanol, which is then converted in the process into acetone. And so that is a very, first of all, even useful byproduct, but also harmless byproduct. And you can see the advantage here that you simply need to use a solvent. You do not have the requirement for gases, or you would not have the requirement for hydride reagents in order to do the reductions. So let's look at some principles and then at some specific examples. I would ask you to recall the lecture on alkyl lithiums and alkyl magnesiums. Look again at the handouts of lecture 3, where we put forward the principles of what carbonyl compound is more reactive, what is less reactive, and where the principal problems or strategies are when we add nucleophiles, and in this particular case, we are going to add hydrides to a carbonyl compound where then the intermediate, the tetrahedral intermediate we are forming, is able in principle to break down to form an aldehyde, which then can undergo reduction again to give us the alcohol. And the general idea is that in principle, if you go from a more reactive to a less reactive carbonyl compound, the reaction should work in the way that you can stop it here. So in the case of an acid chloride, reduction to the aldehyde selectively based on the reactivity of the carbonyl compounds that are involved, the acid chloride reacting more readily with nucleophiles than the aldehyde. This should be possible while in the case of the esters, to stop the reduction on the aldehydes, stage simply based on, again, based on the reactivity of the carbonyl compounds is not possible. So if the aldehyde is forming, it will, in the course of the reaction, it will further react because it's more reactive than the starting ester. And we talked with the alkyl lithium compounds about this, that one way around this might be that this intermediate is stable enough under the reaction conditions the reaction can be stopped here. And in order to effect this, what do we need? It's usually possible if X is not a good leaving group. And also if the metal we have here, if we use metal hydrides, is clinging strongly enough to the oxygen in order to withdraw enough electron density to make the donor capacity of that oxygen not so strong that it pushes out the leaving group here. So strong coordination to oxygen, and then usually sterically bulky ligands, you will see this in a second, help to stop the reaction at this stage. And then only in the workup, breakdown of that intermediate will occur, and this is the way to selectively arrive at the aldehydes. So let's look at some specific examples, some specific reducing agents. Let's start with the one you very well know, lithium aluminum hydride. I have given you in the handouts a whole table which functionalities will be getting reduced to which to where with lithium aluminum hydride. But the bottom line is that lithium aluminum hydride will just reduce about any type of carbonyl group, and so especially esters will be reduced to alcohols. So stopping on the aldehyde stage with lithium aluminum hydride is not possible. And then, of course, having said this, aldehydes as well as ketones will be converted to alcohols. But also one functionality which we had not in the general summary, which is also very useful, epoxides will be also reduced by lithium aluminum hydride under ring opening. And in general, they will react at the less sterically hindered site. Giving the corresponding alcohols here. Also very useful nitriles will go to amines. And also amides will go to amines. And we will look into the reaction mechanism here a little bit later. So just about any double bond which bears a heteroatom is readily reduced. On the other hand, of course, alkenes do not undergo the corresponding reduction reaction. Lithium aluminum being a hard reducing agent will not react with the soft functionality. However, still relatively soft are alkyl halides. So bromides especially, but also chlorides, and also tosylates, they all will undergo reduction to the corresponding hydrocarbon as well. So lithium aluminum hydride, certainly one of the strongest reducing agents you can use. reactions work well, but if you have two functionalities which might in principle undergo reaction with lithium aluminum hydride, you will not achieve any selectivity because it's simply too reactive. Now you can attenuate the reactivity of such a hydride reagents in two ways. You can either exchange the hydride for certain substituents, like you can in lithium aluminum hydride, you can exchange 1, 2, or 3 hydrides, for example, for an alcohol group, and it will become less reactive this way. This is the one way, and we will see an example of this in a moment. The other way is that you can change the counter ion, because the counter ion is playing a major role in terms of that it activates your carbonyl compounds. So lithium being a very good Lewis acid, coordinating well to the carbonyl compound and activating your carbonyl compound for a reaction. But if you change it to a different counter ion, such as sodium borohydride, then the reactivity is dramatically changing. So if you go from lithium aluminum hydride to sodium borohydride, you suddenly have a reagent which is much, much milder than the lithium analog. In fact, sodium borohydride is so much less reactive that reactions can be carried out in water. Don't try this with lithium aluminum hydride. And typically, the reactivity also changes if you look at ester compounds. This is the one thing you should remember here. Sodium borohydride reactions with esters are very slow at best. As a general rule of thumb, you can remember that they practically do not react to whatever you would be expecting here, alcohol or aldehyde. While in contrast to this, aldehyde compounds with sodium borohydride or ketones react well to the corresponding alcohols here. And another class of compounds which works well with sodium borohydride are imines. Which should give you the corresponding amines. And this reaction here is very, very important because it gives you a way to introduce an amino functionality from readily available carbonyl compounds. And so typically what you want to do is you take your carbonyl compound, you convert it with an amine to an imine, and then you're going to reduce it with a mild reducing agent to the amino group. Now, very often it's not so easy to drive reactions all the way to the imines. We have equilibria here. Also, isolation is not so easy. So ideally, what you would like to do is you would like to do this in one pot. However, this process, as I have written it here, would not be possible in a one-pot reaction. You cannot take the aldehyde, the amine, in the presence of sodium borohydride and hope that you will get the amino compound out of this. The problem is that the aldehyde reacts also very readily with sodium borohydride itself to form the alcohol. However, and here we come to the second modification one can do, if you exchange in your borohydride, if you exchange one of the hydrides for a cyano group, sodium cyanoborohydride is the reagent. This will react with aldehydes as well to form the corresponding alcohols. However, and here another factor comes in, the reduction power is pH dependent. So if you have a relatively acidic pH activating your carbonyl compound, sodium borohydride will react. At pH 6, however, no reaction will occur. And now this is something you can use in a very interesting way. Because if you now mix this, your aldehyde, with an amine to form in situ the imine, and as crazy as this sounds, this reaction works best if you have a moderate acidic pH. You know, of course, it's somehow almost contradictory, right? Because the amine, of course, is very basic, so that is preferentially protonated. At this pH, of course, it's still more or less in equilibrium. Then the protonation, the acidic pH, will also help to activate your carbonyl compound. So this way, you create quite effectively your imine, which under these pH conditions, and here's the trick why you need the acidic pH, will also be in equilibrium with the iminium cation. And the iminium cation at this pH will indeed react with sodium borocyanohydrate. To give you the amine. So that's a very powerful method, but you have to do it right. You have to keep very careful control of your pH. You want to have it acidic, otherwise no reaction will occur. But you want to keep it at a low acidity. You don't want to have the high acidity. But then you can mix aldehyde, amine, and your reducing agent all in one pot, and you will get out the amine. And so this process is called reductive amination. And it's arguably one of the most powerful and best methods to synthesize amino groups. Now let's look at another example with sodium borohydride. And let me introduce another variation. If you have an alpha-beta unsaturated ketone, like cyclopentanone, we have in principle the possibility that the hydride can react here And we all know that this is the soft spot of the alpha-beta unsaturated ketone. All can react here, which would be the heart center. Now, interestingly enough, the sodium borohydride, apparently the reduction on the double bond occurs very rapidly, so that you will, in the end, get as a product not only the alcohol you might expect here, but you also get the reduction of the double bond. Very effective process, and it works basically quantitatively. What you can do here is, in order to make your hydride reagents harder, because that is obviously what you need in order not to have it undergo the conjugate addition, it has been discovered that if you add cerium trichloride, cerium is a rare earth metal, however, it's not so rare as the name might make you think. Cerium has extremely high oxophilicity, like all rare earth metals have. And so this is coordinating to the oxygen and tremendously activating it. And in this combination, you will indeed only get the reduction to the allylic alcohol. This is a reagent which has been developed by Lusch, and so therefore it's often referred to as the Lusch reduction. And of course, to keep that chemoselectivity scheme here in place, if you selectively would like to reduce the double bond and leave the carbonyl compound alone, you could revert to the classical palladium catalyst on charcoal. In order to only affect the carbon-carbon double bond. So you can see here that with the reagent combination, you have very powerful tools, in this case where you have two reducible functionalities to affect selectively any type of reduction you can imagine here. Now these rare earth metals like cerium chloride have have another interesting feature. And this is if you treat an aldehyde with such a strong Lewis acid, in the presence of an alcohol, a reaction you also know quite well will quite readily occur. And this is that you will affect ketalization, as you would have expected if you would have formulated this by acid catalysis. Now, this can be used in a very interesting and imaginative way. Let's look at this example here. Let's look at a substrate which has three functionalities which you could, in principle, reduce. We have an ester group, we have an aldehyde group, and we have a keto group. So as we know that the aldehyde here should be most reactive, followed by, this would be here in the middle, medium reactivity, and this should be the least reactive part of the molecule for a reduction reaction. However, if you do now this protocol, sodium borohydride, Cerium Trichloride, and you do it in a mixture of ethanol and water, minus 15 degrees, this is not only the most reactive functionality for reduction, but it is also the most reactive functionality for ketalization. And ketalization can occur either with the alcohol, as I formulated here, but you can form in the same way the hydrate as well. And what happens now, apparently quite effectively, is that this carbonyl compound is in situ protected as an acetal. And therefore, the product you obtain here after workup is that you will reduce selectively this functionality here, and this has not reacted. So I think this is a pretty amazing case that you even, so far we always say we go from the more reactive to the less reactive, and then we might be able to stop reactions here or no. Here we have a case where we can actually tolerate a more reactive functionality and get selectively the less reactive functionality to work. Okay, let's look at another very important reducing agent, and this is called diol. This is diisobutyl aluminum hydride. And this is a reagent which is also, like lithium aluminum hydride, is able to react with ester groups. However, in difference to lithium aluminum hydride, where the lithium is a strong Lewis acid and relatively weak coordinating Lewis acid, activating the carbonyl compound, and then hydride is delivered from the LH4 anion. Here we have the case that the aluminum hydride will coordinate to oxygen and deliver the hydride in this fashion. So you form this intermediate, and again, let's recall the difference here. With lithium aluminum hydride, you have a lithium cation, which is doing the activation. And then you have this anion here, which is converting or bringing this over. And the big difference between these two intermediates is that this is stable at low temperature, and this is not stable. So this intermediate immediately breaks down, forms the aldehyde, and ultimately reacts further to give the alcohol. While this intermediate will stay. And so only on workup with water and acid, this intermediate will break down. However, then there's of course no hydride present any longer. So here you will selectively create the aldehyde. So that's probably, diol has been proven to be the most reliable way to convert esters directly into aldehydes. Nevertheless, you have to do low temperature conditions. You have to still control your reaction quite carefully. This is why you still see very often when people do reaction sequences that it is preferred to do, nevertheless, the reduction to the alcohol and reoxidize to the aldehyde with the oxidation reagents you have seen in the oxidation lecture, rather than trying to achieve that reduction selectively. But especially on small scales, where it's easy to keep low temperature conditions very accurately, you can do this conversion in that manner I've shown you here. And diol is also very useful in the reduction of nitriles. So again, here you add the hydride to your nitrile, but again, this intermediate is stable. It will not, at the reaction conditions, it will not break down before workup, and then only upon workup you are able to convert then under hydrolysis conditions the intermediate to the corresponding aldehyde. And again, in difference here, if you would have used lithium aluminum hydride, this intermediate undergoes further reaction by hydride. And in this case, you would have created the amine. So again, by choosing the appropriate reducing agent, you are able to achieve selective reductions here. So let's look at another interesting case. Let's look at a case like this. Again, in principle, three functionalities which we could consider for reduction. We have an ester group, we have a carboxylic acid group, and we have an alkene. So of course, hard reducing agents should go here. Soft reducing agents should preferentially hydrogenate the double bond. However, you also know that the carboxylic acid functionality is probably the least reactive functionality within the carbonyl derivative when it comes to addition of nucleophiles. Nevertheless, there's a reagent, and this is simple borane, which will selectively reduce the carboxylic acid rather than reacting with the ester. And again, the reason that works can be understood in the reaction mechanism. So the carboxylic acid functionality is the least reactive derivative if it comes to adding nucleophiles to the carbonyl group. But on the other hand, the carboxylic acid, and especially the carboxylate, is the strongest nucleophile. So what is happening here initially is that the borane will react with the carboxylic acid in the way that this reacts as a nucleophile, borane reacts as an electrophile. And so let me just abbreviate the rest of the molecule here with an R. So what is happening is that the carboxylic acid attacks the borane, hydrogen is forming. This is happening a total of 3 times. And so you form such a carboxylate first. And this now is greatly activated, because you have a Lewis acidic group here, is greatly activated for further reduction. And so with borane, now this will undergo selectively the reduction, and then the intermediate aldehyde derivative, which forms, again, reacts further and forms the alcohol. So this is a very good way. Borane, however, itself is a gas, so it's not so easy to work with this. But there are ways around this. You can create borane in situ if you use lithium borohydride and iodine. You form lithium iodide, HI, and borane in situ, which will immediately react with your carboxylic acid and then create the corresponding alcohol. Extremely good method, very nice. Works also very nicely with another important class of compounds. And these are amino acids. Very often, there are many applications of amino alcohols. And very often, you start from readily available amino acids out of the chiral pool and would like to convert them directly to the amino alcohols. And one way is to first form the methyl ester here and then do the reaction with lithium aluminum hydride. But you can directly use this protocol. And again, commonly, you will create the borane in situ in order to have your reagent going. So this way, let me show you another concept of reduction, which we already briefly mentioned. And this is the transfer hydrogenation. This is a reaction which is known for a long time already. And there's a process called the Merwine-Pondorf-Valley reaction, where you take a carbonyl compound and you take aluminum, an alcoholate of aluminum, here in this case of the tris isopropyl compound. You do this in isopropanol. And you will establish basically an equilibrium of your reduced alcohol and the isopropanolate will get oxidized in the process forming acetone. And the way this works from a mechanistic point of view is, as so often, we have our carbonyl compound here. Now aluminum is coordinating to it. On the aluminum we have our tris isopropyl groups. And now this hydrogen from the isopropyl group is actually being transferred. You see, this is where the oxidation then takes place. So this is being transferred. This is coming here, and then here this bond goes in, and so you can see you form this part then gets oxidized, this part gets reduced, and this is how the two products are forming. And so you again see it's a well-ordered transition state, 6-membered ring transition state, reorganization of 6 electrons, so again the typical aromatic transition state, and this is why this reaction works very well. However, what you have to do here is you have to use stoichiometric amounts of your aluminum compound. Or even more specific, you have to use it in excess, because it's overall it's in equilibrium. And in order to drive the equilibrium, you need to use your aluminum alcoholate in excess in order to get the alcohol and the acetone rather than having it on this side. And this, of course, although aluminum is a very inexpensive material, however, you shouldn't say it this way. We have large amounts of this on Earth. However, to make aluminum, you use a lot of energy. So although it is present in abundance, to use it is not, or is very energy efficient. It's not very energy efficient. So newer type of developments have now been able to replace the stoichiometric reagents with ruthenium catalysts, which, without going too much into detail here, these are ruthenium amine complexes. So we have a ruthenium 2 here, complexes, and they are able to affect in the same way like the aluminum isopropoxide is doing is, they are able to affect this type of reduction in the same way. However, you only need this catalytic you still need an excess of your isopropanol, which is your reducing agent. But you are able to do this very efficiently with catalytic amounts of methyl. And this is not only a reaction which works for simple reduction of ketones. People have been able to introduce groups here in order to have stereocenters here. And you can see if you reduce a ketone, you form a secondary alcohol, which is chiral. So you're interested in controlling the stereochemistry here. And this is possible if you use chiral variants of these ruthenium catalysts. And so not only that you can, in a very efficient manner using isopropanol now affect carbonyl reductions, you can also do it in an asymmetric way. And these developments go back to the work of Professor Noyori. And as you know, he received the Nobel Prize in the year 2001 for his work on reduction chemistry. So with this, let's look at some stereoselectivity issues. In typical cases, you often have in reductions are cases of inducing with the reduction a new stereocenter here, very often in the neighborhood of a chiral center. Now we covered this extensively, so please recall the Falcon-Arn rule here. You have in script, you have it in the script of the first lecture to this. So this is a case which we have already covered. And also the Cram-Chelate model. Another thing I would like you to recall, which is also already in the script on stereoelectronic effects. However, I've put that example again also in this script, is the hydride attack to cyclic carbonyl compounds, where in principle there's a possibility of axial attack, or equatorial attack. Which leads to two different diastereomers, and the axial attack is sterically disfavored because your nucleophile has to come in on a trajectory which interferes with these two axial hydrogens here. The equatorial attack does not have that problem. With the equatorial attack, however, we have the problem that this carbonyl group, as it becomes axial, because we have an equatorial attack here, the hydroxyl group, the carbonyl group becomes axial, it has to move, it has to pass by this equatorial hydrogen here. It's bisecting in the moment these two hydrogens. If it stays equatorial, it just dips a little bit down, but it does not have to eclipse any of these two hydrogen. If it moves up, it has to eclipse this hydrogen on its way, and therefore this builds up torsional strain. Torsional strain in the transition state, and therefore the general rule is that small nucleophiles will attack axial, large nucleophiles will attack equatorial. Small nucleophiles, because they are not really hindered by the axial hydrogens here, and therefore the steric interaction is not as severe. Large nucleophiles are hindered by the hydrogens here, so they come equatorial. However, if they come equatorial, torsional strain is built up. So it looks like that if the steric hindrance is not here, to avoid this steric strain, the torsional strain, the axial position is preferred. And to have a concrete example, this reaction here, if you do the reaction with lithium aluminum hydride, I should have it somewhere on my table. It gives you a selectivity for about 9:1 for the axial attack. If you start switching this, what looks like it might be a little bit bigger, lithium aluminum hydride, where 3 of the hydrides are displaced by T-butoxide. Apparently that is still not, it's somewhat bigger, but it's still not big enough to change the trajectory, certainly because aluminum hydride, aluminum oxygen bonds are quite long. So the steric influence of these T-butoxide group is apparently not big enough. However, if then you choose a boro reagent which has again a secondary butyl group, as we have seen in diol, the same group. Now boron hydrogen bonds much shorter, boron carbon bonds much shorter, so the steric influence is certainly more felt here. Then you actually reverse the selectivity almost completely here. So again, very interesting case that by the appropriate choice of your reducing agent, you can have pretty large effects in your stereoselectivity. And let me show you another interesting case for this. Let's look at one last case for today. Let's look at the reduction of a beta-hydroxy carbonyl compound. And you know these compounds, of course, very well. These are products of an aldol reaction. And we have seen methods how to create aldols in a stereoselective manner. Now, if you do a reduction of this carbonyl compound, in principle, there are two products which can form. You can either, you're creating a new stereocenter here, and the hydroxyl group can either be on the same side like your first hydroxyl group, so this would be the syn diastereomer, or you can create the anti-diastereomer. Now, this structural element is extremely important because in many biological active drugs and also in many natural products, this structural element is occurring. Nature has decided to make compounds of this type in a large variety, and this is because nature is using acetyl coenzyme A. It's transferring acetyl groups one by one and is reducing them afterwards. So you have acetyl group, acetyl group, acetyl groups, and then the carbonyl groups get reduced, and you're creating this structural element. So it's important to be also able to create this structural element by synthesis. And there are actually two interesting mechanisms you can think about this. If you draw your diol in what is starting here in a chair-like conformation, and if this is coordinated now by some kind of metal, you have that controlled arrangement where placing these groups in equatorial position is favored. Now keep in mind here and convince you when you look at this example at home that this stereocenter here is of course given. So please see if you agree that this stereocenter is indeed the right representation of what I've drawn here. I cannot simply say I put this in the equatorial position. I have to put it in the right way. However, if I would have started with the opposite stereoisomer, I would have mirrored this representation, having the stereocenter here, and then again are able to put it in an equatorial position. But keep in mind that you're not free here, that the stereocenter that you have here has to be represented here correctly. Now, if we have an arrangement like this, if a hydride reagent would react now with this carbonyl compound, it would clearly prefer attack here from this axial position, because then basically no rearrangement of that arrangement has to occur. So you see already the chair is pre-organized. The hydrogen comes into the missing position here. And this type of arrangement leads to the syn diastereomer. However, there's a second way to think about this. And let me do the exact same arrangement here with one difference. And this difference is that the metal could already have the hydride which is delivered for reduction. Now, if this is the case, and we want to have a chair-type orientation, in order to deliver this, I have to flip the carbonyl group. So that the delivery could come from here. And again, I would like you that you convince yourself that this will lead to the anti-product here. But I believe what is easily seen is that the hydride attack from this side is clearly opposite to if I flip this up and the hydride comes from the other side. So this, I hope you recognize immediately that now going from this model to this model, we are approaching the carbonyl group from the two different sides. So this is nice for a model. Now, do we have reagents for this? And indeed, we have. In order to have this type of situation, the reagent which has been developed is triethylborane. So the triethyl borane will simply coordinate here with the two oxygen functionalities, shooting out one molecule of ethane here, so that we have two ethyl groups left here. So this becomes borane. And as an external reducing agent, sodium borohydride is employed. And what this simply is doing is the borane is activating by chelation this carbonyl group, and then the hydride will attack from as is shown here. And if you use sodium borohydride alone, and what is actually done is one uses a less reactive reagent than sodium borohydride. So again, in this sodium borohydride, 3 hydrides are displaced by acetoxy groups. This is an even milder reagent like sodium borohydride. We already have seen cyanoborohydride in the reductive amination. So very often, that's the trick. You take sodium borohydride, you add 3 equivalents of acetic acid, you exchange 3 hydrides for this ligand, and then it becomes an even milder reagent. And this will react in this mode and give you exclusively the anti-diastereomer. This is a highly reproducive and reliable method to create these type of reactions. And as I say, this is widely used in pharmaceutical industry and drug industry because this is such an important structural element. Okay, with this, I would like to wish you a very good weekend. There's a tutorial on the electrocyclic reactions already in the net. So over the weekend, weather will be bad. You have nothing to do but solve this, and then we see us on Monday.